and welcome to this revision video. This is for AQA alkanes. My name is Chris Harris and I'm from AlleryTutors.com, and basically we're just going to go through the just a quick overview of the topic of alkanes, just to make sure that you've covered the topic reasonably well. Like I say, it's just an overview. You do need to practice, obviously, using your past papers. Also, the PowerPoint that I'm going to use on here, you can purchase it as well, so you can use it for your revision, which could be pretty useful. You print it out and annotate it, add notes, etc. So we're gonna you can get access to this on the link in the description box just below the video. So if you have a look at the link, click on it, and then you'll be able to get a hold of the video. Like I say, this video is specific to the AQA specification, and there's the specific points that was taken from the AQA specification that links in with this PowerPoint. Okay, so let's make a start. Alkanes. Okay, so they have a general formula of CnH2n plus 2, where obviously N is just the number of carbons. These are saturated. That means they've got loads and loads of hydrogens. There's no double bonds in these molecules. Okay, so they are basically hydrocarbons. They contain hydrogen and carbon only, which makes it a little bit obvious. They're saturated. Each carbon bond is bonded 4 times. No double bonds in here. Here's some examples. You've got methane, CH4, ethane is C2H6, and then you've got propane there, which is for 3 carbons. So you've got cycloalkanes as well, which are a little bit different. They actually have the same general formula as an alkene with a double bond, with 1 double bond, which is CnH2n. They are still a cycloalkane though, because they don't have any double bonds. They are still alkanes. But as long as you're aware of that, that's obviously quite important. Obviously, these are functional group isomers of alkenes. And they are, like I say, they're still saturated. So, because they don't have that alkene group. Okay. So, right. So that's basically what an alkane is. They make really good fuels, actually. Obviously, you can burn them, which you'll find out in a minute. Okay. So, fractional distillation. Okay. So, we need to know, obviously, the kind of practical technique of this. So alkanes are found in crude oil, okay, which is a mixture of different length hydrocarbons. So crude oil is obviously the stuff you dig out from the ground. It's got loads and loads of different hydrocarbons in there, all different lengths. And we're going to use a fractional distillation column to separate this. So what happens first is the crude oil is vaporized. So we heat it up to about 350 degrees Celsius, and it turns into a gas. And this is obviously in this bit here, and obviously the furnace would then heat that up. And then the vaporized oil enters the column, so it's going in through here, and rises through the trays. The longest hydrocarbons don't vaporize, and they run to the bottom. So your longest hydrocarbons run down into the here, and they collect in a slurry. This is this bit here. Whereas your ones which are gases, because they've been heated, remember, will start to rise up the column. Okay, so now this is really, really important, because obviously we've got to be able to separate these different hydrocarbon lengths. And basically the column has a temperature gradient. That means as we go up towards the top of the column, it's cooler, and towards the bottom of the column, it's warmer. And actually what we get is the vapor rises. When it rises, it condenses at these different temperatures. And this is because the chain length is different in the hydrocarbons that we're vaporizing. So basically your shorter chains come off at the top because they've got the lowest boiling point, and actually they're still gases at this point, whereas your longer chain ones, like down here, will condense to a liquid, maybe at a higher temperature, and so they would collect on these trays here. Okay, and basically you draw off these fractions, you get the fractions that come off. That's why we call it fractional distillation. So the shortest hydrocarbon, like I say, won't even condense. These are just gases. This is at 20 degrees. This is about room temperature, or just under room temperature. So these come off at the top of the column. Okay, you can see your different length hydrocarbons here. So 40 plus carbons. You look at it about your lubricating oil, your paraffin, wax, asphalt, which is just tarmac, and then your gases, obviously methane, butane, things like this. These are 1 to 4 carbons. Petrol comes off here. Diesel oil is what you would use, and fuel oil is what you use in ships. Okay, so you'd like really heavy oil. So the fractions can be used in loads of different ways. Like I say, so gas is used in LPG, liquefied petroleum gas, so it stands for, and stove gas. Petrol is obviously used in cars. Kerosene is used in jet fuel. It can be used in heating as well. Diesel oil used as to fuel diesel trains. So obviously they need like a heavier one. Fuel oil is used in ships and power stations, so much higher energy in these. And bitumen, which is used, or asphalt, which is used in roofing and tarmac. So this is much thicker. Okay, cracking. Right, this is really important in the petrochemicals industry. What you get when you dig your oil out of the ground, you might find that you have lots of heavy fractions, your long chain fractions. Problem is, these things are not as popular as your short chain fractions. When I say popular, I mean they're in lower demand. So we're looking for higher demand fractions, and luckily, if we've got a longer chain hydrocarbon, we can crack these into more valuable, lighter fractions. So, like I say, it produces a variety of heavier demand fractions, which are in kind of lower demand, and each fraction varies. Obviously, it is kind of a bit random in some respects. You don't know exactly what you're getting from under the ground. So heavier fractions, like I say, like fuel oil, are in lower demand than your lighter fractions, which are petrol. These are a lot more valuable. We can take the heavier ones and we can crack them. Basically, it just means breaking them into shorter hydrocarbon chains, which are more valuable. So here's an example of an equation. So we've got dodecane, which is C12H26. So that is your long 12 carbon chain that can be broken down into decane and ethene. Notice we produce an alkene and an alkane. Okay, you don't produce two alkanes. So basically, there are two types of cracking. We have thermal cracking, we have catalytic cracking. And obviously we need to know the two different types. Okay, so let's look at thermal cracking first. Now, as the name suggests, obviously we're going to be using heat. So we use a high temperature and pressure for thermal cracking. 1,000 degrees Celsius and 70 atmospheres of pressure in particular. And basically the products of thermal cracking are mainly alkenes. Now, it's not so much of a bad thing, because actually these alkenes can be used to make polymers, which is plastics. So, for example, propene is used to make polypropene. The other type of catalytic cracking, is catalytic cracking. And again, as the name suggests, we're using a catalyst. Now, the difference with this one, because we're using a catalyst, the temperature is still high, but it's not as high as thermal cracking, but the pressure is lower. Okay, so we use a zeolite catalyst. And the zeolite catalyst is like a honeycomb structure. Basically, this helps to lower the temperature needed. And then products of catalytic cracking are mainly aromatic hydrocarbons, useful in fuels for vehicles. Okay, so that's pretty important. And aromatic compounds contain benzene rings, which is 6 carbons in a ring with a delocalized electron system. So, like I say, these things are aromatics, which are like benzenes, like I say, little benzene rings. But these are really useful in fuels. They are actually carcinogenic, so you've got to be careful with them as well. And if we use a zeolite catalyst, this basically lowers the temperature and the pressure needed. So it's a lower cost and it speeds the reaction up. So catalytic cracking is mainly used for petrols, making petrols. Thermal cracking is pretty good if you're going to make alkenes to make plastics. Okay, let's look at combustion of alkanes, because obviously alkanes, as we know, are used as fuels. So alkanes, they burn in oxygen completely, which means you have a plentiful supply of oxygen. They form carbon dioxide and water, so these are your combustion products. And basically they're good fuels, they burn readily, they produce lots of energy, and that's exactly what you want in a fuel. And they're used to power vehicles, obviously you use petrol and diesel, and we can make electricity as well. So some electricity is made using gas, burning gas or oil power stations as well. Obviously we can get coal as well. So we're going to complete the you may be asked, to complete a reaction or an equation to show the complete combustion of a reaction. In this case, we're going to use butane, and all you have to do is just make sure, however many carbons you've got here, you must have the same number of molecules of carbon dioxide, because that's the only place where the carbon comes from. And then if you look at your hydrogens here, just put, obviously we've got 10 hydrogens, so we need 5 H2O. And then what you do, once you balance these, then you balance your oxygens to make sure it balances. But you always produce carbon dioxide and water in these reactions. Okay, incomplete combustion. So this is basically when we get an alkane and we burn a limited supply of oxygen. Now the problem with these is we produce a multitude of different products. Carbon monoxide and soot are just two of them. And obviously these are not very good for your health. So just to show you two examples of these reactions, incomplete combustion, we can burn it and we can produce carbon monoxide. So the top equation there shows the incomplete combustion of carbon monoxide, of a fuel to produce carbon monoxide. So we still produce water, which is fine. Sometimes we can get a reaction where we produce carbon monoxide and a bit of carbon dioxide. Basically, this reaction is just showing you how that would fit as well. Now, carbon monoxide is poisonous. It bonds to hemoglobin in your blood, and this prevents oxygen from bonding. Now, this isn't obviously very good because you want the oxygen to be carried by the red blood cells. If carbon monoxide sitting there, you're obviously going to have an oxygen deficiency. And you can remove that carbon monoxide by using a catalytic converter. And they put these in the car, and it basically reacts the carbon monoxide with oxygen, oxidizes it effectively, and produces carbon dioxide, which is less harmful to humans. You can also produce soot, like I say, and soot is just carbon, just pure carbon. So here's the reaction showing that. So this is basically, again, we've just got butane here, burning it to produce carbon and 5 lots of water as well. So you can see here we've got really very little oxygen compared to methane used. And soot obviously makes things dirty. Okay, so it causes breathing problems, makes buildings dirty, clogs up engines because these particulates get stuck in the engine. You'll have filters in a car to help try to remove or stop this soot from causing too many problems. Okay, right. So on the topic of burning fuels, obviously when we burn a fuel, mainly completely, obviously we do produce complete combustion. It's very rare to get 100% complete, but we can get reactions which are produce large amounts of this carbon dioxide, and this obviously leads to global warming. So burning fossil fuels produces carbon dioxide. It's a greenhouse gas, and these basically work by absorbing infrared radiation from the sun, and which is obviously heat. This is heat from the sun. But what it does, it emits some of this radiation back into the earth, and we call this a greenhouse effect. So it's like a warming effect. This is basically infrared or heat not being able or not being allowed to escape from the earth because the carbon dioxide is trapping it. So most scientists do argue that the increasing amounts of carbon dioxide is leading to an increase in global temperatures, and this is obviously what they call global warming, and they monitor things like in this picture, this is a glacier obviously retreating or melting. You can see you've got snow melt here, obviously melting into this pool of water here. So this could be evidence for a warming Earth, and most scientists argue that it's carbon dioxide that's causing it. Photochemical smog. Now ozone can cause this photochemical smog at lower levels. So basically, again, this is linked to the burning of fossil fuels such as alkanes. So ozone occurs in the lowest level of the atmosphere. And this exists as sunlight, hydrocarbon, and nitrogen dioxide mixed to form the ozone at the lower level. Okay. Now your hydrocarbons obviously is the fuel that we're burning, and nitrogen dioxide is formed when we burn a fuel. So we've got enough heat and pressure, we can form nitrogen dioxide. So a great deal of hydrocarbons and nitrogen dioxide, like I said, come from cars and factories. And when these solid particulates and ozone mix, we create this thing called photochemical smog. And this picture here in particular shows some photochemical smog in China in particular. This is a picture taken in Shanghai. You can see obviously the skyscrapers of Shanghai there, and just misted over with photochemical smog. And obviously there's quite a few cities, not just Shanghai, there's a few cities globally that have this problem with photochemical smog. And obviously there's rules and regulations and politicians trying to come up with strategies to try and reduce air pollution. Okay, so photochemical smog, what it does, it harms the respiratory system, which isn't any good. This is in animals and humans as well. Obviously, we're classed as an animal. So, and ozone is toxic as well. We don't want ozone in the lower atmosphere. We want it in the upper atmosphere. So, ozone is not very good for us either. Like I say, the oxides of nitrogen, like I said here before, these are caused by nitrogen and oxygen that's naturally found in the air, reacting under high pressure and temperature of the engine, and they produce this nitrogen dioxide gas. And obviously this isn't very good either. It's acidic, and we don't want to breathe this stuff in. But thankfully, catalytic converters, they can help remove or reduce the amount of unburnt hydrocarbons that haven't quite burnt in the engine, And they can prevent the oxides of nitrogen from going into the atmosphere, because we can react them and try and reduce the levels of them. But it's really difficult because obviously we're producing loads of different gases here. And obviously as engines get better and better, we're even now looking at electric cars in the UK in particular, and it's a way of trying to reduce the harmful emissions from car vehicles. Okay, so from vehicles or cars, I should say. Acid rain. Right, we talked a little bit about this. So when we're burning a fossil fuel, we release sulfur dioxide, nitrate, oxides of nitrogen as well can cause acid rain. Now, obviously, this is going to cause a problem because it damages trees. As you can see in this picture, this is a forest that's been damaged by acid rain. Obviously, you can see the bark's been stripped off and the leaves. There's no leaves on the trees. So these cause harm to plants and fish as well. And obviously erode buildings that we live in. So yeah, some fossil fuels, they contain these sulfur-based impurities, and when we burn this fossil fuel, the sulfur reacts with the oxygen and it forms sulfur dioxide. And obviously this sulfur dioxide is an acidic gas, rises up into the atmosphere. If it gets up there, mixes with the water and forms sulfuric acid, which then falls as acid rain. Again, oxides of nitrogen do the same. So if we can remove this sulfur dioxide, in particular from things like chimneys in factories, we can use a process called wet scrubbing. And this is basically where we're using an alkali to neutralize the sulfur dioxide in the flue gases. And by doing that, obviously, we can form compounds which actually we can use. We can use it to make plasterboard, etc. Okay, so basically how it works is we just dissolve the calcium carbonate, which is just an alkaline solution, alkaline solid, and we dissolve it in water or an oxide. To be honest, it can work with either, and we just spray it onto the acidic gases leaving the chimney, and it effectively reacts with the sulfur dioxide, neutralizes it, and it's removing the sulfur dioxide or reducing the amount that goes into the atmosphere, which also should reduce acid rain. Okay, so let's look at some free radical reactions. In the introduction to organic chemistry video, if you've seen that, obviously we looked at the mechanisms, and we said that mechanisms contain curly hours, apart from the free radical reactions, which we don't need to do for AQA. So basically, the chain reaction involves three main stages. We've got an initiation, a propagation, a termination step, and we're just going to show obviously each of these stages. So initiation is basically, this is where radicals are produced, normally using visible light or ultraviolet, so you can use UV. These are called photochemical reactions, and basically the bond breaks and we produce two radicals. Propagation is like the middle step of this step, and I'll show you some reactions in a minute to show you where they fit. Propagation is basically where we've got a radical meeting with a non-radical, they react, new radicals are formed, and these then go on to react with other non-radicals. So we call this a chain reaction because it literally just keeps going and going and going until we get to a termination step. So termination is when we get two radicals that collide, and this ends the chain reaction because what you form is a non-radical molecule which is more stable than a free radical. Okay, now this is really useful because actually what we can do is we can use alkanes. Alkanes are notoriously unreactive. They don't react with anything. So to get an alkane to react with something, we really need to either heat it up or we can use free radicals. And free radicals are super reactive species, and these react with the alkane and they form new products from that. So this is where it all fits in. Okay, so in particular, we're going to use alkanes to make halogenoalkanes. Okay, so chloromethane can be made via this reaction. So we've got methane reacting it with chlorine. There's a bit of the UV light there as well. Look, this is going to get involved. And we produce our chloromethane and HCl. So we can use a free radical mechanism to make this. So the initiation step. So sunlight breaks the Cl bond. Okay, the Cl-Cl bond. This is called photodissociation. It's just a posh word for breaking a bond using light, effectively. So the bond breaks equally, and we produce two highly reactive radicals. So let's have a look. There it is there. So we've got Cl, Cl, there's the bond, bit of UV, and we produce two Cl radicals. Now, these dots here symbolize a radical. A radical is just an atom with an unpaired electron in it. In other words, it could be just a chlorine atom, which is just the same thing. Okay, propagation. Okay, so this is the next stage. So basically the Cl radical reacts with a methane molecule to make a methyl radical, which is CH3 dot. Then the methyl radical reacts with the Cl2 molecule, and that forms chloromethane and a Cl dot radical. And then the Cl radical can then react with more methane. So let's look at them step by step. There's the methane, there's the Cl dot radical. What this does is this reacts with the methane, and the radical gets passed along onto CH3 dots to form CH3 dots and HCl. Now, because this is so reactive, this is then used in the second propagation step. There it is. So we drag this down here. So always the radical in the first step is the reactant in the second step. This reacts with more chlorine, which is unreacted chlorine, Cl2. And what we form is your product, CH3Cl, and your radical, Cl dot. Now, the product of step 2 must be the radical product of step 2 must be the radical reactant of step 1. So these must match. Okay, so the little tricks to making sure you're writing the right thing. And you can see we formed our haloalkane, which is our halogenoalkane. And the final step is termination. This is when we get two radicals react and they make a stable non-radical molecule. So for example, forming bromomethane, for example. Or you can use this one, which we're going to use chloromethane instead. So it doesn't really matter. So this one is obviously, here's your methyl group, methyl radical and a chloride radical. And these are going to collide to form your chloromethane there. Okay, so this is basically just showing a termination. You can have a few termination steps. Obviously, any two radicals, any radicals that collide, they will terminate and they will form a non-radical, which is more stable. So if there's loads of Cl dot though, loads of chlorine radicals, then what we get is multiple substitution. So we get di, tri, tetrahaloalkane, and basically we don't get basically get this pure product. But if we don't, then all we get is we just get the single substitution. So if we've got very little of the chloride radical knocking around, then we just get the mono substituted one. But if we've got loads of it, like an excess, then we get dichloro, trichloro, tetrachloro, and it just keeps going and substituting. And that's it. That's the end of the topic to do with alkanes. As you can see, it's just a very quick overview. There's bits on there to radicals, which are pretty important. There's a lot in there about green chemistry as well, about sulfur dioxide and global warming and all that kind of stuff. So make sure you're obviously able to do that. And obviously we're looking at things like fractional distillation as well and cracking, so which is the petrochemical industry. But like I say, these PowerPoints are available to purchase. If you just click on the link in the description box below this video, you should be able to get them from there. That's it. Bye bye.